Okay, so what we want to talk about now is we're going to move on from Newton's third law and pulleys and stuff like that, and we're going to talk about a different style of problem. We're going to talk about friction. Let's pump some iron. Woo! Okay. So here I've got a 20-pound weight, and what I'm wondering is these dumbbells, typically the material here is made out of like a kind of like a hardened plastic, but it's a little bit rubbery, okay? So because it's a little bit rubbery, when I take it and when I put it on the countertop, do you expect the fact that it's rubbery, do you expect there to be more friction or less friction than if it was some smooth polished metal? Okay, okay, are we good with that? So because it's made out of some sort of a rubbery surface, then we expect there to be more friction. And indeed, if I try and take my hand and I try and push on it a little bit, I'm applying a pretty significant force, and it's not budging, right? Whereas if I was applying that force to a metal thing, it would slide. It would actually slide considerably easier. Why is that? Why is one surface, right? Why is one material on this surface going to be more frictiony than another material on the surface? Josh? Yeah, that's a really good idea. It's like, is this material is more rough than that material? Rufus? Would the fact that it has a certain weight, would that make it easier or harder to do it? Well, okay, let's ask that question. Let's perform an experiment, okay? So can I have a volunteer to come up here for me, please? Yeah? Sammy, come on up here, okay? So what I want you to do is I want you to try and push this right now and just see, like, how much force does it take for you to push it so that it starts to move? So go ahead. There we go. Okay. Now what I want you to do is I want you to take this and I want you to push on the bottom one, and you tell me, does it take more or less force than before?
It takes more force.
It takes more force. Now what I want you to do is go ahead and push it now. Oh, you can do it. That's pretty good. So what do you think? More or less force than before?
More force.
More force. Why is that? Thank you very much. You can have a seat. Why is that? Why is it that when we have more weight stacked on top of here, it takes a greater force for us to push on it? Rufus? Is gravity affecting it more? Is gravity affecting this block more? Okay. Is gravity affecting this block more? Is the force of gravity changed on this block? Has the force of gravity on this block changed? No. What's force of gravity equal to? Mass times acceleration due to gravity. Did I change the mass of this thing? Did I change the acceleration due to gravity of the Earth? No. So gravity is not affecting this block any more or less than it was before. Did I apply, Josh, did I apply force on this thing? Yeah, absolutely I did, right? Okay. Riddle me this, okay? Here's another thought experiment. Imagine, so I'm trying to push on it, right? Imagine I lift up on the block. Is that going to change the force of gravity on the block? No, but it's an additional force, right? It is going to change the net force, okay? So what I'm wondering is, if I push on it and if I lift up on it, not lift it off the bench top, if I lift up on it, is it going to make it easier or harder for me to move this object? Oh. So there's two different ideas at play here right now. One is, why is one material more frictiony than the other? And the other one is, well, why does the amount of vertical force on this thing affect how frictiony it is? And so that's what we're going to talk about right now. So first of all, there are two types of friction. One is called static friction, and the other one is called kinetic friction. Static friction is when an object is static, so it's not in motion, and you try and shove it, it's going to feel some sort of frictional force that resists your push. So static friction is the frictional force between an object and its surface that it's resting on. When the object is at rest. We're going to draw a picture, and then we're going to draw in like a zoomed in picture. So here's a really simplified version of my diagram, or of what we have going on here. Imagine this thing was just a rubber box. I just happen to have a weight because that's what I can borrow from the school really easily, okay? So imagine we had an object, and it's sitting on a surface. And what we're going to do is we're going to zoom in. We're going to zoom in on this surface. Do you understand what I'm doing here? Yeah, we're zooming in. Ooh, you get it? Yeah, we're zooming in. So there's two surfaces at play here. There's the object, and it's sitting on the countertop. The object, is this object, if I looked at the bottom of it with like a microscope, would you say the object's surface was perfectly 100% smooth? No. So the weight, the object, it's got a surface that's a little bit rough. If I looked at a microscope, and if I looked at the surface of this countertop, is the countertop perfectly 100% smooth? No, it's not. And so there's another surface, right? So this is the box or the weight or the whatever, okay? And then on the bottom, this is the ground or the surface or the countertop or the whatever, right? And this is the object. When they're just sitting there together, what can the little undulations of the object, what can they do with the undulations of the surface? Yeah, they can kind of interlock with each other. Wow, what a great term. Would you agree? So they can kind of like impress into each other, right? So because they can impress into each other, because they can kind of interlock with each other, this is like, I don't know, have you ever tried to push something that had wheels, but you were pushing it on the grass? Do you know what I'm talking about? So like something that should roll really nice and easily on a hard, flat surface, but as soon as you get to the grass, then the wheels, what do the wheels get to do in the grass? They like dig into the grass, right? They form an indent, and then all of a sudden, if you try and push it out, you got to push it up this hill, up this little indent. That's what you're doing. Every single time an object is at rest, all the tiny little imperfections, they're pushed into an indent in the surface. So if you want to start to get this thing going, then you got to push them up on top of the little indents. Does that make sense? So the static friction as an observation in reality, like what we observe, static friction is always harder to overcome than kinetic friction. So let's talk about why are some materials harder to push than other materials, right? If this was polished steel or polished metal, would the surface of the object be more rough or more smooth? It would be more smooth, right? And so do you think it would have a higher force of friction or a lower force of friction? It would have a lower force of friction. Also, think about this for a second. Because this is like rubberized plastic, is the rubberized plastic, is it a little bit soft or is it really, 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 really hard? It's a little bit soft. So what does that mean? This undulation right here, can it make like an indent in the material? Can it maybe kind of compress the material and make those indents a little bit deeper? But if you had a really, really hard surface, like polished steel, if you put that on the ground or on the bench top, are the little undulations of the bench top, are they hard enough to force impressions into the hardened steel? No. So the hardened steel is going to slide on top of those imperfections, and it's not going to force its way into that. Does that make sense? So the material it has something to do with it clearly, but even polished steel has imperfections. Any surface, there is no perfectly flat surface. That's not physically possible. I mean, it is possible if you individually put atoms, but then even then, an atom has a shape to it, right? So whatever, that's fine. Why is it that when I push down on this thing, it's harder to push? It's harder to get it to start accelerating. Because what am I doing to this undulation in that depression? What am I doing to that little undulation that's on the bottom of the box? What am I doing to it? Yeah, I'm deforming it even more, right? I'm causing those depressions, those peaks and valleys, to be even larger than they normally would. So now, instead of getting out of a little tiny divot, you're getting out of a really big divot. It's way harder to get out of that big divot. I don't know, does that make sense? So there are two factors at play here. So static friction is determined by two factors. The first one, and it's pretty obvious, it's the materials involved, right? Both surfaces come into play. If this was steel on steel, it would slide really easily. If it was rubber on rubber, it would not slide easily at all, right? So it's the materials that the two surfaces are made up of, And then also the other one, and I'm going to give it away here. It's the normal force that the surface is applying on that object. Okay? Now let's think of a really simple example. We're not going to use numbers at all, okay? So let's say I add an object, and if I'm not pushing down on the object, and if I'm not pulling up on the object, what can you say about the force of gravity and the normal force on the object? They're equal and opposite, right? They're balanced, okay? But here's the problem. If I add another force, if I put a force applied here, what does the normal force have to do in order to compensate for that extra downward force? It has to increase. So now the normal force has to increase. Would you agree, by me pushing down on it, the bench has to push up even harder than it was before? And that's what determines the force of friction. Okay? Let's do another example. Okay? If I have an object, again, force of gravity and normal force are equal if I'm not doing anything. What happens if I lift up on the object? If I add an applied force like this, F applied, right? What does the normal force have to do in order to compensate for that? It has to decrease. What if I'm the one matching the force of gravity? What if I pick up on this with exactly the weight of the object? What all of a sudden happens? Rufus? Yeah, well, what's going to happen to this object if I pull up with exactly the weight, right? So instead, force of gravity and the force applied are equal. What can you say about the normal force on this object? Right? There is none. It's zero. Does that make sense? So I'm totally compensating for the weight of this thing. Now all of a sudden, like, it's basically not on the countertop at all, right? So there should be no force of friction because there is no normal force. So the more you pull up on it, the less of a normal force is required to keep it on the countertop. The more you push down, the higher the normal force has to be in order to compensate for that. So that's the idea behind it. Okay, now there's another force of friction. That's static friction. That's when the two objects are not in motion relative to each other. The second type of friction is kinetic. Kinetic friction is just the force of friction when an object, and we have to be very clear about the wording that we're going to use. This object has to be sliding. Do you understand what I mean by that? It's not rolling, it's sliding when the object slides on a surface. Okay, so what does this actually look like? If you were to graph how much force is required to be able to like push an object, let's go ahead and make ourselves a graph. So we're going to graph the force of friction versus the applied force for an object. And we're not going to put any numbers in here because it totally depends on. Yes. That's totally fine. Sorry about that. Sometimes I go too fast. Okay, so let's take our object and let's try and push on it just a little bit, okay? Okay, so right now, what's the force of friction on this object? What's the force of friction on the object? It's 0. Does that make sense? Is there any force that it's opposing right now? No. So I'm not touching it, so the force of friction is 0. Now, I'm going to apply a tiny little force. Is the force of friction tiny or really humongous right now? Tiny. The force of friction can change. It depends on what force you're applying on the object. Does that make sense? It's matching my force. So no force, no force. A little bit of force, a little bit of force. A lot of force, it's matching a lot of force. But eventually, I'm going to be able to overcome it. So what happens is if I apply no force, then there is no force of friction. Put an X there. If I apply a little bit of force, it matches my little bit of force. So put an X there. If I apply a lot of force, depending on the properties, depending on the materials and the normal force and stuff like that, it can also match my lot of force. So put an X there. Hopefully I'm trying to go in a straight line. I'm trying my very best, okay? So what's going to happen is it's matching me this whole time. Boom, 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 boom. It's matching me until I get, would you agree, there's some maximum force of friction here that I can overcome. So there's going to be a maximum force of friction that I can overcome. And then when it starts to slide, now that the object's sliding, those undulations, they don't have time to sink into each other. Does that make sense? They're just kind of going on the surface. So is the kinetic friction going to be greater or less than the static friction? It's going to be less because it's kind of hopping on top of those undulations. So what happens is once you hit your maximum static friction, then all of a sudden, as soon as it starts to move, the force of friction that it pushes back on you drops. And then it stays constant no matter what force you apply. So this is what happens. Boom, it's linear all the way up to some maximum amount, and then it drops, and then it stays constant. Can you see the two different sections in this graph? What's the first section, this slanty bit? Is that static or kinetic friction? So this whole section here, that's force of friction static. It's matching your force up to a maximum. This is the maximum force of friction static. And then here, this section, that's just our force of friction kinetic. Okay. Again, the numbers depend on the materials and the normal force, if you're applying any force down on it or pulling up on it, whatever. Any questions about that? Is this actually a little bit intuitive? Like, does this kind of immediately make sense for a lot of these concepts? I think it is fairly intuitive, so that helps, okay? Okay, so here's a conclusion that we can make. We have to be able to write an equation that takes into account the materials. And what's the other thing it has to take into account? The normal force. Good. So the force of friction. And we're going to say the absolute value of the force of friction. Do you know what I mean by absolute value? We don't care if it's negative or positive. We don't care what direction it's going, because the direction totally depends on the context of the situation, right? So the force of friction is equal to some constant. I know this sucks, but this is the Greek letter mu. Okay? Often written as a U, but with like a line at the beginning. But this is the way I was taught how to do it. Okay? It's mu times the normal force. As the normal force goes up, so does the force of friction. As our mu goes up, so does the force of friction. Now, again, this is the Greek letter mu. That's how you spell mu. Not Mewtwo, okay? Mu. I know, that sucks. It's called the coefficient of friction between the surfaces. And it's totally different depending on the surfaces. This is how we take into account the difference in surfaces. So how do you get the coefficient of friction? Well, you have to look it up in a table or something like that. So you go ahead and write that down, sure, whatever, but let's go ahead and look up. Okay, sorry, mu is the coefficient of friction between the surfaces, okay. So let's go ahead and look up the coefficient of static friction between, what two surfaces do you want? Rubber and steel. Boom. Okay, uh-oh, engineers, uh-oh. So we take a look at it, right? And there's a whole table here. Whoa! There's a material and what material it's going against, right? And so the higher, oh man, the higher this number goes, the higher this coefficient goes, right? Coefficient of friction. Do you think a high coefficient of friction means hard to push or easy to push? Does a high coefficient of friction mean hard to push or easy to push? It means hard to push, really hard to push. So we're going to find rubber, blah, 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 blah. We got to keep going. Oh, here we go. Okay. Rubber, whatever. And a 60A belt against tool steel. Interesting. It's got a coefficient of friction of 0.86, not 0.86. Okay. Interesting, silver against silver is 1.4. That's really high. Okay. Human skin against metals, that's a weird one, 0.9. Okay, we're going to move on. I don't know. I'm sure engineers need all sorts of information for all sorts of things that I have no idea about. I don't know. I don't know if that's just that's just a quick way for them to do it, like 0.85, 0.9, 0.8, whatever. I don't know. They're just being lazy. Chemists and physicists are notorious for being lazy, so it wouldn't surprise me if engineers were equally as lazy or lazier, because engineers, by and large, are a pretty smart group of people, so that means that they get to be pretty lazy. Okay, so here's the deal. We're going to go through an example, and we can get it done. That's totally fine, and then we're going to continue this conversation tomorrow. But I'm not going to give you any practice today because it's just a discussion mostly. So let's talk about an example. A 250-gram object sitting on a rough horizontal surface. Requires, man, why do I keep doing that? A force of 7.9 newtons to move. And the 7.9 newtons, we're going to assume the force is in the horizontal direction. So what we want to know is, what is the coefficient of static friction between the object and the surface? But that should be obvious. Okay, so 250 grams is pretty small, and 7.9 newtons is actually a fairly large force for such a small object. So this is a lot like us doing rubber, but it's kind of like rubber on rubber. That's essentially what we're talking about. We're going to have a fairly large coefficient, but that's fine, no big deal. So how do we go about solving this thing? Well, coefficient of static friction. What is coefficient of static friction related to?